Hi friends, I'm sure you've played with magnets. You might have some fridge magnets on your refrigerator. Did you know that your earphones also contain magnets? So if you bring the earphones close to each other, you'll notice that they repel each other. In this video, we are going to explore magnetism, magnetic fields, and pattern of magnetic field lines. I'm going to make the topic of magnetism really easy for you. And after you watch this video, try solving the quiz and the top 3 questions on this topic. Links are given below the video. Magnetism has been known since ancient times. A magnet is an object that has a special property to attract certain materials, such as iron, steel, nickel, and cobalt. Now I'm going to take this magnet near these things and let's see which things get attracted to the magnet. Based on that, you can guess which material they are made of. So let's start with the nail. As you can see, the magnet can attract this nail. What material is this nail made of? That's right, iron. Next, let's bring the magnet near this clip. And the clip gets attracted to the magnet. What material is the clip made of? Correct, steel. Now let's try the spoon. The spoon does not get attracted by the magnet. What is the material here? The spoon is made of stainless steel. Note that steel is attracted by a magnet, but not stainless steel. The watch is not attracted by the magnet. The watch is also made of stainless steel. Now I'm going to take this magnet near these 2 nails that look very similar, and let's see what happens. As you can see, only one nail is attracted to the magnet. The nail that is attracted to the magnet is made of steel. The other nail is not attracted by the magnet because it's made of stainless steel. So we can use a magnet to differentiate between steel and stainless steel. As you may know, magnets have 2 poles, North Pole and South Pole. In this magnet, the poles are at the 2 ends of the magnet. But how do we know which one is the North Pole and which one is the South Pole? If this magnet is suspended freely using a string, then the pole that points towards the north direction is called the North Pole, and the pole that points towards the south direction is the South Pole. Now magnets can be of different shapes. A magnet of this shape is called a bar magnet. This is a horseshoe magnet and this is a disc magnet. In a bar magnet, this is the North Pole and this is the South Pole. In a horseshoe magnet, this white dot at the end is the North Pole and the other end is the South Pole. And in a disc magnet, it's like a coin. So this end is the North Pole, and if you flip it, this end will be the South Pole of the magnet. Now let me ask you, can a magnet have a single pole? Can a monopole exist? That's right, a monopole cannot exist. A magnet must have 2 poles. For example, if you break a magnet into 2 parts, each part will have 2 poles, a North Pole and a South Pole. Now, as you may know, like poles repel each other. So if I bring another bar magnet like this, as you can see here, the North Pole of the 2 magnets are repelling each other. Similarly, the 2 South Poles will also repel each other. And unlike poles attract each other. As you can see, the North Pole of this magnet attracts the South Pole. Do you know what happens when this magnet attracts the iron nail? The magnet first induces opposite poles on the iron nail. So the South Pole of the magnet attracts the North Pole on the iron nail. That's how magnets attract objects, by inducing opposite polarity on the object. And so we say induction precedes attraction. Let's place the properties of a magnet and magnets of different shapes on our concept board. Now let's talk about magnetic field. You may have heard about other fields such as gravitational field and electric field. Field is an area or region where an object experiences a force. For example, when I lift this clip to a height, as you can see, it falls down. This clip is pulled down by the Earth's gravitational force. So there's a gravitational field here that pulls the objects down. Similarly, a magnet has a magnetic field around it. So when we place this magnet near this clip, as you can see, it experiences a force and gets attracted towards the magnet. This means that the magnetic field is strong near the magnet and it becomes weak far away from the magnet. The strength of the magnetic field decreases as the distance from the magnet increases. A magnetic field can be visualized using magnetic field lines. The pattern of the magnetic field lines tell us the shape of the magnetic field. Now, how can we find the shape of the magnetic field? There are two ways: using iron filings and a magnetic compass. First, let's discuss the iron filings method. Now, let's say you have a bar magnet like this. Now, place a thick paper over the bar magnet and sprinkle a thin layer of iron filings over the paper, and then tap the paper gently. The iron filings arrange themselves in a regular pattern that looks something like this. This pattern gives us a rough idea of the shape of the magnetic field of this bar magnet. Now, the other method is to use a magnetic compass to plot the magnetic field lines. I'm sure you've seen a magnetic compass before. It looks something like this. Do you know how a magnetic compass is made? The magnetic needle in the compass is made using a tiny magnet, and it is pivoted so that it can move freely. This red part of the magnetic needle is the north pole, and it points towards the north direction. And this end is the south pole, and it points towards the south direction. Even if we shake or move this magnetic compass, the magnetic needle automatically aligns itself to point in the north-south direction. Do you know why? That's right, because the Earth has a magnetic field, and so this magnetic needle is aligning itself along the Earth's magnetic field. We'll talk more about the Earth's magnetic field later in the video. The magnetic compass is also called a plotting compass. Let's see how we can use this magnetic compass to plot the magnetic field lines of this bar magnet. Let's put this bar magnet in the center. Now let's put the magnetic compass here. The direction of the magnetic field is the direction in which the north pole of a magnet experiences a force. As you can see here, the north pole of this compass is being pushed away by the north pole of the bar magnet. So the direction of the magnetic field is the direction in which the compass needle points. Here the compass needle is pointing in this direction. So the magnetic field is in this direction. Now I am going to move the compass to a different point. As you can see, it points in a different direction. So the magnetic field here is along this direction. We need to keep moving the compass to different points around this bar magnet, and we will get the magnetic field direction at those points. Now we just need to join these lines using curved lines. If we keep repeating this exercise and move the magnetic compass on the table, we will get more magnetic field lines. And here is the shape of the magnetic field for the bar magnet. We need to mark the magnetic field lines with arrows, since magnetic field lines have a direction from the north pole to the south pole of the magnet. If we use a horseshoe magnet, then the magnetic field lines will look something like this. As you can see, the pattern of the magnetic field lines depends on the shape of the magnet. As we saw, The magnetic field lines give us the pattern of the magnetic field. Now let's look more closely at the field lines and discuss their properties. We'll use the magnetic field lines of a bar magnet to discuss the properties. The first property is that the magnetic field lines start from the North Pole and end at the South Pole. As you can see, the direction of the magnetic field lines outside the magnet is from the North Pole to the South Pole, and it's shown by the arrows here. But inside the magnetic field lines are from the South Pole to the North Pole. The second property is that the magnetic field lines come close to one another near the poles of the magnet. They are densely packed at the poles, but the field lines are more widely separated at other places. When the magnetic field lines are close to each other, do you know what does it indicate? That's right, the magnetic field is strong when the field lines are close to each other. As you can see here, the magnetic field is stronger near the poles of the magnet, and it gets weaker as we move away from the poles. The third property is that the magnetic field lines do not intersect each other. They may come close to each other, but the magnetic field lines will never cross each other. We can prove this point with a simple example. Let's say two magnetic field lines intersect each other. Now if you place a magnetic compass at the point of intersection, then in which direction will the compass needle point? Along the first magnetic field line or the second one? It's not possible for the compass needle to point in two directions. So this proves the point that magnetic field lines can never intersect each other. Let's place the properties of a magnetic field on our concept board. Now let's talk about the Earth's magnetic field. We know that the Earth has a magnetic field all around it. Since when we use a magnetic compass, it automatically points in the north direction. Or if you take a freely suspended magnet, then the north pole of the magnet will automatically point towards the north direction. This is in the absence of any other magnet. So it's the Earth's magnetic field that aligns the compass. The shape of the Earth's magnetic field resembles that of an imaginary bar magnet that is buried in the center of the Earth. Do you know what is the polarity of this imaginary bar magnet in the Earth? We know that the north pole of the magnetic compass points towards the geographical north. So what pole of the Earth's magnet is in the geographical north? That's right, it's the South Pole, because unlike poles, they attract each other. The South Pole of the Earth's magnet, which is in the geographical north, it attracts the North Pole of the magnetic compass. Similarly, the North Pole of the Earth's magnet is in the geographical south, because it attracts the South Pole of the magnetic compass. So remember, the magnetic South Pole is near the geographical north, and the magnetic North Pole is near the geographical south. So they are opposite. Now one thing to note is that the axis of the Earth's magnet and the geographical axis, they do not coincide with each other. The axis of the Earth's magnetic field is inclined at an angle of about 15 degrees with the geographical axis. So a freely suspended magnet or a magnetic needle makes an angle of about 15 degrees with the geographical axis, and so it points to the approximate north-south direction. How strong is the Earth's magnetic field? Do you know what is the SI unit used to measure magnetic field? That's right, the SI unit is Tesla, and the symbol is T. The magnetic field of a bar magnet is about 0.01 Tesla, and the average value of the Earth's magnetic field on the surface of the Earth is only about 50 microtesla. So the magnetic field near a bar magnet is about 200 times stronger compared to the Earth's magnetic field on the surface of the Earth. So the magnetic field on the surface of the Earth is pretty weak. Now what would happen if magically the Earth's magnetic field became very strong? Imagine all the iron objects being attracted towards the Earth. It reminds me of a scene from the Iron Man movie where all the iron objects get attracted towards him. As we discussed, it seems that the Earth has a bar magnet placed inside it. But actually, there is no real magnet inside the Earth. So how does Earth get its magnetism? It's due to the magnetic effect of electric current. The electric currents are due to the motion of convection currents of molten iron in the Earth's outer core. And the electric currents produce magnetism. So the Earth is like a huge electromagnet. Now the topic of magnetic effect of electric current and electromagnets will be discussed in a separate video. Let's place the Earth's magnetic field on our concept board. I hope the concept of magnetism is crystal clear to you now. Magnets are used in so many things. For example, fridge magnets, in speakers, earphones. Did you know that computer hard drives store data using magnetism? And next time when you go to buy some stainless steel item, you can always check if it's really stainless steel using a magnet. Because as we saw, steel gets attracted by a magnet, but not stainless steel. And to revise these concepts, just go to my website manochaacademy.com and try the quiz and the top 3 questions for this video. To make it easy, I'll put the links below. So just click on the links and try the quiz and write your answers for the top 3 questions. I promise to reply to your answers as soon as possible. And do remember to like, comment and share this video. And if you haven't subscribed to my YouTube channel already, go hit the subscribe button right now and click the notification bell so that you can get notified about new videos. You can also check my Facebook page and do check out my website manochaacademy.com for more videos like these and for the quiz and the top 3 questions on this video. Thanks for watching.